discuss specific plans. Okay, it's 7 p.m., so let's go ahead and get started today. All right, so good evening, everyone. How's everyone doing today? So it's our last virtual meeting together. So it's slightly less sad than kind of a normal in-person meeting because I'm in my living room and you're all just names on my computer screen. But you know, this will be kind of the last time, so there's still a bit of sadness. So hopefully everyone's doing okay. You know, hopefully you guys are handling your final exams, final projects okay. So the plan for today is we're not going to cover any new material, so we're just going to just review for the final. So I took a look at the poll kind of right before we came to lecture now, and the number one thing that people want to see was we're going to review turbulence. The second thing people wanted to see was instabilities. So that was kind of the two most recent topics that we covered. So I'm definitely happy to go over that. And then the number three thing, if we have time at the end, was conservation law. So that was kind of like finite volume problems and with conservation of mass energy. Okay. So before we get started, I know that there's a lot of questions on problem 2 on the homework regarding Rayleigh's criterion and Furtop's theorems. So I'm going to ask kind of, you know, if you guys have questions on problem 2 to hold that off until we reach that point. We cover instability. So I want to make sure I focus on that because that's probably one of the more practical things of instabilities that we can cover. So besides problem 2 on the homework, are there any questions that I can answer before we get started today? Number 3 on the homework. Okay. We'll say so number 3 is also a okay. Yeah, number 3 is also an instability problem, so we can cover that when we go to instabilities. Okay. All right. So the question is, are we going to have a turbulence problem solving in the final? So if you looked at the study guide, you'll notice that for the problem solving learning objectives, I left turbulence off that. So what that means is that there's going to be no problem solving problem based on turbulence on the final exam. So the only thing I'm going to ask you on the final exam based on turbulence is going to be just conceptual stuff. So it's going to be a little bit heavy. It's going to be a bit heavy loaded. So I'll tell you right now, out of the 6 short answer questions on the final, 3 of them are going to be turbulence. Just because I'm not going to ask you a problem solving one. Just because because of the lockdown, I basically had to cut basically half the things that I had planned for turbulence. So I wanted to make sure I give you guys the conceptual stuff, which I think ultimately is more useful for practical use, because a lot of times you're not going to be performing hand calculation for turbulence. And so because we didn't really do any problems in class, I'm only going to ask you conceptual stuff on turbulence. All right. Any other questions regarding the final or anything else? Okay. So let's go ahead and get started. So let's start with turbulence. Okay. So we did basically 3 class sessions of turbulence, and kind of like we mentioned, I kind of just basically talked about kind of the most general things. Okay. So to kind of sum it up in a few words, kind of the things that I want you to take away from turbulence are just its general characteristics. And so the other thing I want you to take away is just the idea of the energy cascade. So what that means and what that, kind of the physical meaning behind that. Okay. I want you to know about the Reynolds stresses, kind of what those represent and, why those appear. Okay. And let's see. And then I also want you to know kind of just conceptually what we covered on Monday, which is the stuff on turbulence model. Okay. So let's kind of go over kind of those kind of big 3 umbrella topics and kind of discuss and kind of review what they mean. Okay. So let's start with general characteristics. So we know turbulent flow, we kind of present it as kind of like the foil or the opposite of laminar flow. So while laminar flow is kind of the nice, well-behaved school kid, the one that you want to bring home to mom, turbulent flow is kind of the big rowdy kid that, is always causing trouble. So on kind of the first day we talked about turbulence, we talked about kind of 5 different characteristics. So kind of the first characteristic that defines turbulent flow is the fluctuations. And so what I mean by that are, you know, turbulent flow, they're known for having kind of this really chaotic motion. And the thing that kind of drives that motion are these kind of random fluctuations. So instead of the fluid kind of going in a nice orderly path like it is in a laminar flow, what can happen is that you can have, you know, fluctuations where the fluid kind of just jumps around kind of all like this in every which direction. So that's kind of the first thing that people generally associate with turbulence is kind of this, this really kind of random motion that's driven by the fluctuations. And so the next characteristic of turbulence is nonlinearity. Okay? And so we know that turbulence generally occurs when the Reynolds number is really, really high. And we know that when the Reynolds number is really high, that flow tends to be driven by inertia. So it's called an inertia-dominated flow. Okay? And so what that means is that the convection terms, which are on kind of the left side of your Navier-Stokes, which also happen to be the nonlinear terms, those tend to dominate in your solution. So because turbulent flows are extremely inertial, they're also extremely nonlinear because those convection terms are going to dominate. So the next one that we went over was vorticity. Okay, and so the way vorticity factors into turbulence is that we know that in turbulent flow, you know, a lot of different flow structures of different sizes form. And one of kind of the most prominent flow structures that form is a turbulent eddy. So an eddy is kind of like a pocket of kind of swirling flow. And so the way that we kind of characterize that swirling flow in those eddies is with vorticity. So, you know, vorticity and turbulence kind of go hand in hand because, you know, a lot of the flow structures that appear in turbulence are, can be described with vorticity. Okay. Next is dissipation. So when you compare turbulent flow to laminar flow, what tends to happen because you have that energy cascade, you have the kinetic energy of your turbulent flow. It tends to dissipate into heat at a much higher rate than laminar flow, and so that's because, you know, you have these kind of flow structures that appear that are very tiny that make it kind of very easy for it to dissipate flow. So kind of what we talked about before is that if you want to have a turbulent flow and you want to sustain it, basically to kind of offset this dissipation of kinetic energy, you basically need to keep supplying it with some kind of mechanical energy. So you need to have some kind of pump or some kind of, you know, atmospheric, you know, forcing to kind of overcome this dissipation. Okay. And so the last characteristic that we talked about was diffusivity. Okay. And so diffusivity means, you know, things like momentum and mass and energy, those tend to mix better in your turbulent flow. Okay. So diffusivity is kind of the same thing as mixing. So we kind of know, or we kind of, you know, just intuitively know that, you know, when you have a turbulent flow and it's really chaotic, that tends to mix stuff a lot better than laminar flow, right? Like if you want to mix the milk in your coffee, you don't kind of stir it slowly and kind of nice, even patterns. You take your stir it, you kind of stir the crap out of your coffee in order for it to mix most efficiently. So for applications where you need kind of efficient mixing and strong mixing, you're gonna want to have turbulent flow because that's gonna enhance it. Okay. All right. Any questions on the general characteristics of turbulent flow? Okay, so now let's talk about the next big thing, which is the energy cascade. Or the other way that the notes describe it is turbulent production. Okay. And so, you know, kind of what we mentioned before, when you have turbulent flow, what tends to happen is you have these flow structures of many different sizes, right? So if you remember kind of this figure that I drew in the notes before, where you have kind of turbulent flow in a pipe, you might have some flow structures that are really big like this, okay? So this is what we call a large eddy. So it's large because it kind of takes up the entire kind of spatial dimension of the flow, where this is kind of the diameter. So in addition to the large eddy, you can have like smaller eddies too. And these can be, you know, lots of different sizes. And so this is kind of a really defining characteristic of turbulent flow, because if you have laminar flow, you don't have these kind of varying flow structures. What you have is just kind of one flow structure, and that's usually defined by your geometry. Okay? But because you have turbulent flow, you have these kind of big flow structures, and then those break apart into smaller ones. Okay? And the reason for that is that even though these big structures tend to form in turbulent flow, they're actually unstable. And so by unstable, what that means is it can't really retain its form. So even though you might have a big eddy that forms like this, it usually doesn't last for long, because what tends to happen is that because of the kind of inertial processes, this big eddy kind of spawns, you know, two smaller eddies. So kind of visually it might look like this. You have kind of a big eddy like this, okay? And then it's going to break apart, and it's going to break apart into two baby eddies. Okay. And so, and as you can imagine, you know, these small eddies will break up into even smaller ones. Okay. And then this process tends to continue until you reach the eddies of the smallest sizes. Okay. All right. Any questions on this? Right, so the question is, what causes the breaking up again? So the breaking up is caused by purely inertial forces. So basically, what happens is that, you know, you might have these kind of flow structures that form momentarily, but you also still have kind of chaotic flow that's kind of coursing through these guys. Okay? And so because you have this chaotic flow that's kind of going through them, that tends to kind of disrupt this eddy and kind of break it up into smaller ones. So you know, just the kind of any formation of any kind of flow structure is kind of almost immediately broken apart by the chaotic flow field. And so that in turn kind of breaks up other ones and stuff like that. So it's kind of a very kind of chaotic process and very coupled process that goes on. But primarily they're broken apart by inertial forces from the mean flow. Yep. Okay. And so whenever you know, you have these large eddies and they break up into smaller ones, the way that we usually describe that is that we say that the kinetic energy from the big eddies are being passed to the smaller eddies. And that kind of phrasing is kind of key to understand the energy cascade. Okay. And so intuitively, the way that you can think of this is that, or kind of the way that I think about it in my mind is that, you know, if we have kind of like an energy bin, okay? So this is kind of oversimplifying it, but I kind of find it useful. Because we know from conservation of energy that energy can't be created or destroyed, right? So let's say at the beginning, we have this much energy in our large eddies, and we only have this much energy in the small ones. And so through the energy cascade, or through kind of the breaking up of the large eddies into smaller ones, all this, a lot of this energy in the large eddies will get transferred into the smaller eddies. Okay. And so when I say that the kinetic energy from the big energy gets passed down to smaller ones, you can kind of think of it like this. So the large eddies, the energy, the kinetic energy that it had from motion, it basically takes, that energy is basically taken and kind of transported into the smaller eddies, just like that. Okay. Any questions on this? Okay. And so this process of the eddies breaking up will basically continue until you reach the smallest eddies. And so how do we know when we reach the smallest eddies? Usually we know because the size of these eddies are on what's called the Kolmogorov scale. Okay. And so what that means is that if we compute kind of the local Reynolds number of the smallest eddies, where we take the velocity and we take eta, where eta, remember, is our Kolmogorov length scale, and we divide by the viscosity. So usually for a given flow, the velocity is somewhat fixed because that's kind of driven by your macroscopic factors. The viscosity is fixed, so that usually you can't change because that's a property of the fluid. So once this length or this eta gets small enough such that the Reynolds number gets close to 1, those are kind of the size of the smallest eddies in our model. Okay. And so once we reach the smallest scales, something magical happens, and which is kind of different up to this point, because we know that this breakup of big eddies to smaller ones, this is purely an inertial process. So viscosity hasn't actually factored in yet. Okay. So the only place where viscosity actually factors into turbulent flow is once we reach the smallest eddies. Okay. And just from the Reynolds number, we can see that because we kind of, you know, as a theme in this class, we know that when the Reynolds number is close to 1 or it's lower, then we know viscous effects are going to become dominant. And so before, what we examined was kind of the overall Reynolds number for the general flow. But for turbulent flow, since you have all these flow structures of different sizes, you know, if we look at just the local Reynolds number of just the smallest flow structures, and if that's close to 1, then that's enough for viscosity to come into effect. Okay? And the effect that viscosity has at these smallest length scales is that of dissipation. Okay? And so once we've kind of reached these smallest length scales, the way viscosity comes in is that it dissipates this kinetic energy as heat. Okay. All right. Any questions on the energy cascade? Okay. So now let's go to the kind of the next big topic in turbulence, which was the Reynolds stresses. Okay, so if you remember, you know, the way that we got the Reynolds stresses was they showed up in our Reynolds average Navier-Stokes, you know, the other name for that equation is known as the Rand's equations. Okay? And so the Reynolds stresses, they appear as kind of an additional stress for our fluid. Okay? And you know, the reason why we call it a stress is that the Reynolds stresses are a way, or it's the way that these turbulent fluctuations will affect the momentum of the mean flow. Okay. Because remember, a lot of times when we're solving turbulent flow equations, we kind of recognize that the fluctuations are there, but oftentimes we don't really care we don't really care enough about them to solve for them explicitly. But what we do care about is how are those fluctuations going to affect our mean flow, where our mean flow kind of describes kind of the bulk motion of our flow. And so after we kind of plugged in our Reynolds decomposition into Navier-Stokes, and we kind of worked through the terms, we ended up with kind of an extra term there that's not in our classic Navier-Stokes, and that was the Reynolds stresses. And so the functional form of that looked like this. So the functional form of that was basically we have our turbulent fluctuations, which is our U primes. Okay? So remember, we used the prime notation to denote fluctuations. And so if we take our two turbulent fluctuation vectors, we took an outer product. So we basically took these two vectors and turned it into a tensor, a rank 2 tensor. And then we take that entire quantity and we average it. Remember this overbar notation denotes an average. Okay. And so by doing that, this is the form of the Reynolds stresses. Okay? And so we didn't actually do much to actually compute it, because a lot of times it's impossible. Because remember, the turbulent equations aren't closed. But what I do want you to know is basically what the Reynolds stresses physically represent. And so kind of in a nutshell, what the Reynolds stresses represent is the fact that when you have a turbulent fluctuation and you have fluid that basically jumps in kind of random directions, when those fluid particles move, they also take their momentum with it. And so what happens is that when a particle or a turbulent fluctuation jumps from one layer of the fluid to another, it takes its momentum. You know, that's, you know, and once that fluid particle kind of joins a different region of the fluid, then that the original momentum of that fluid will basically mix with the new momentum of its different part, and then through that you basically get a mixing of momentum. And so what this basically means is that this is a way for the turbulent fluctuations to basically transport momentum in your fluid. Okay? So visually, it looks something like this. So let's say that we have some kind of a boundary layer flow. And so we know in the boundary layer, our velocity is going to vary pretty rapidly at that. So it's going to be kind of 0 at the wall and high up there. Okay? And so if this were purely laminar, then we would basically, the fluid would only go in the horizontal direction. So it would basically just stay in its lane and kind of just flow in just one layer. Okay? But due to turbulence, what can happen is that you can have fluid particles that go from this layer up here, where up here we say that the momentum is fairly high because our velocity is high. And then due to the turbulent fluctuations, it can jump down from the top down to the bottom, just because, you know, in turbulence, we kind of have this random motion. Okay? And so by jumping from one layer to the other one, this particle is going from a region of high momentum to a region of low momentum. And so because of that, you know, the momentum, the high momentum is going to mix with the low momentum, and you kind of have this mixing of momentum. And kind of the net effect of this is that you kind of have an external force, and that external force is characterized by the Reynolds stresses. All right, so question. So when the momentum of the mean flow is affected, that somehow induces a stress in the fluid or the boundaries? Yes. Yeah, so basically the momentum of the mean flow is going to be affected, and kind of the net effect of that is a stress. So it's not actually like a true stress. Like it's not like a physical, it's not something that's, you know, like pressure is something physical that you can do to a fluid, and like viscous stress is something physical that you can do to a fluid. So, you know, the turbulent fluctuations is actually the fluid itself. So it's kind of causing a mixing of momentum, but the way that you can kind of formalize that mathematically is through a stress term, because it kind of has the same net effect as like a viscous stress or like a pressure stress. Yeah. All right, any more questions on Reynolds stresses? What is that YouTube video? Oh, okay. Yeah, well, I'll check it out later. Okay, so that's Reynolds stresses. Okay. So now let's talk about Eddy Viscosity or turbulence modeling. And so if you remember, you know, when we talk about turbulent flow, the equations of motion are actually really difficult to solve because we don't have enough equations to solve for the unknowns. Okay? And so what we need to do instead, or what we need to do in order to solve these equations, is we need to basically include some more equations to solve for the turbulent quantities. And so there's lots of different turbulent models out there. So there's kind of lots of different flavors, mostly kind of depending on how you were trained and who their favorite models were. So we kind of only went through one in detail, and that was the Eddy viscosity theory. Okay. So the idea behind Eddy viscosity theory is that we basically are going to imagine that the turbulent Reynolds stresses are just going to be adding an additional viscosity to our equations. Okay. And so the parameter that we basically are solving for is that we're solving instead of solving for the Reynolds stresses, which requires a solution of two kind of turbulent velocity vectors. What we can say is that instead of that, what we can solve for is just a single scalar, and that scalar is just going to be a turbulent viscosity or Eddy viscosity. Okay. And so, you know, kind of formally, what we're saying is that instead of this, where this guy on the left is our Reynolds stresses. So that's a nasty piece of math that we often don't want to solve for in general. So what we can say instead is that due to eddy viscosity theory, we can say that this is going to be equal to nu t, which is our eddy viscosity, times the gradient of our mean flow. Okay, and so this is really huge because you know, remember we're not directly interested in solving for the turbulent fluctuations. What we're interested in instead is just the gradient, is the behavior of the mean flow. And so through this eddy viscosity theory, we can basically we have a relationship between the turbulent fluctuations, which we don't really care about, and then but we can put those in the form of something in our mean flow, which we do care about. And so after we substitute this back into our governing equations for Navier-Stokes, what we've done is we've basically eliminated all of the turbulent fluctuations from the model, which is good. And then we have just an equation for our mean flow, which is what we wanted. Okay? And so the tricky part of this is that we have to assign this. We have to choose this guy. Okay. So the unfortunate thing is choosing good values for nu t is extremely hard. Because, you know, if you think about kind of the normal viscosity that a fluid has, that's a property of the fluid itself. So remember, you know, we talked about to measure viscosity of a fluid, you can take it into a lab and you can measure it, you can put it under all these different kind of scenarios, and you get kind of an accurate viscosity measurement. The difficult thing about eddy viscosity is that it's not a physical property of the fluid itself, but instead it's a property of your flow. And so by flow, I mean things like your geometry, the speed of the flow, the forces on the flow. So, you know, the flow is actually a much more complicated beast than the fluid itself. And so because the flow depends on a lot of different factors, your eddy viscosity is going to depend on a lot of different factors too. So the ways that you can actually determine that, you know, we didn't actually perform many calculations for this, but, you know, we did talk about kind of two methods in general. So kind of the first method that we talked about was called the mixing length model. And so the nice thing about the mixing length model is that it's known as an algebraic or a zero equation model. So it doesn't require the solution of any differential equations, which is nice because that means it's pretty cheap. But because it's cheap, you know, it's actually not that good. So it's kind of a nice kind of conceptual stepping stone to kind of describe what the eddy viscosity means, but it's not actually used often for any practical calculations. So ones that are more common are ones that solve for the eddy viscosity using some kind of differential equation. And so we went over this kind of at the very end of the lecture on Monday, but kind of some of the most common ones are the two equation models. We basically kind of add two additional unknowns to our problem. Mostly, a lot of times they're the kinetic energy. And the one we went over was called the K epsilon model. Okay. Because in this, in the K epsilon model, what you're basically going to be doing is you're going to be solving two additional differential equations. One of them for K, where K is the turbulent kinetic energy. And then epsilon here, this is our dissipation rate. Okay. And so by solving those two equations kind of in parallel with your Navier-Stokes, from that you can compute your nu t and then plug that back into your Navier-Stokes. So these methods are often a lot more popular, just because they're a lot more accurate. But it's going to be, with the two equation model, they're basically going to be impossible to solve by hand. So basically, the only way to do this is with computational fluid dynamics. Okay. All right. Any questions on eddy viscosity? The question is, eddy viscosity usually larger or smaller than the fluid viscosity? Yeah, it's a good question. So most oftentimes the eddy viscosity is going to be much larger than the fluid viscosity. Right? And the reason for that is because when you have turbulent flow, you know that the Reynolds number is going to be really high. And so if you kind of think of turbulence as kind of an inertial effect, or an effect of due to the Reynolds number being really high, then we know that the viscous effects are going to be really low. So basically anything that's produced by inertia, which is generally viscosity or turbulence is, those effects are going to be much stronger than the regular viscosity. So how much bigger they are, it's going to depend on the flow itself, but it's not uncommon for it to be at least a couple orders of magnitude bigger than the fluid viscosity. Yeah, and kind of the reason for that is because in turbulent flow you have such effective mixing, and so because you have just like you have better energy and mass mixing in turbulent flow, momentum mixing is also greatly enhanced too, and so that's kind of captured in this kind of eddy viscosity. All right, any other questions on eddy viscosity before we move on to instability? Okay. Okay. So that's kind of the big four topics in turbulence. A lot of what we covered in turbulence kind of falls under those four umbrellas. So let's review instability. All right. So we covered instability kind of in the week before turbulence as kind of the lead up of that. Okay. So we kind of just got done talking about turbulence, and we know that turbulence is this kind of state of fluid flow where everything is kind of really chaotic, and really, crazy. But it doesn't get like this kind of instantaneously. So in order to get to turbulent flow, what the flow always has to do is it has to transition to that. And so things don't just happen, things don't just turn turbulent kind of at the snap of the fingers like that. There's kind of a process that goes there. And kind of that first step in that process is you have kind of an instability in the flow that grows. And specifically what I mean is that they grow by time. So visually, and this is kind of just a kind of a simple cartoon of it, but I hope it kind of illustrates that. Because what can happen a lot of times in your fluid flow is that you have a lot of these kind of small, I call them disturbances. Okay? So if you kind of think of like flow in a pipe, the pipe surface is not going to be perfectly machined, that it's going to be completely smooth. You're going to have a lot of little bumps and ridges just because of machining tolerances, and also if it's a pipe that's been in service for a long time, you could have things like fouling and stuff that kind of collects on the pipe. So your surface is going to be a little rough. And so as the fluid kind of flows over this rough surfaces, they're going to introduce disturbances in the velocity. And so what can happen if you have unstable flow is that, you can take these small disturbances, and what can happen sometimes is, one of two things. Okay? So if certain conditions are met, such that the flow is stable, what a stable flow will do is it'll take these small disturbances and it'll damp it out. So instead of that kind of small wiggly wave, what you get in the end is a straight line. So this is stable. And so the terminology that we use to describe that is that we say that the disturbances are going to be damped. Okay? So they basically don't get an opportunity to grow. Okay? So that's kind of the first case. But if you have an unstable situation, what can happen is that if you have this small disturbance, it can actually grow. And just like we mentioned, this situation is known as unstable. And so a lot of what this chapter is kind of devoted to is, is determining what are the conditions that lead to these either stable or unstable situations. Okay? Because if we kind of know more about these kind of the conditions which can trigger these instabilities and have them grow, then we can kind of better understand this and better understand the transition into turbulence. All right, any questions on this? And so from here, I'm going to work a little bit backwards, just because I know there's a lot of interest in the class for looking at problem 2. So problem 2 is of homework 6 that I mean. So problem 2 is about kind of the later half of the lecture notes. Okay. Because if you have a flow, and you a general flow, and you know its velocity distribution. So if you have a flow and you know its velocity distribution, we want to know, is this enough information to tell if it's going to be stable or unstable? And so we went over kind of 2 criteria about this. So the first criteria that we went over was Rayleigh's criterion. And the other criterion, which it seems like everyone that I talk to is scared to say his name, but it's okay. You can pronounce it incorrect. You can pronounce it incorrectly. I don't personally know the guy, and I actually might be butchering his name too. But because I'm the instructor, I have to say it with somewhat confidence. So his theorem is known as Fjortoft's theorem. And so from the velocity distribution, you can basically, what you can do is you can apply these 2 criterion and determine whether the flow is going to be unstable or not, or at least have the possibility of becoming unstable. Okay? So let's go over Rayleigh's criterion first. Okay? And kind of the long name for Rayleigh's criterion is Rayleigh's inflection point criterion. And so what Rayleigh's inflection point criteria says is that if there is an inflection point in the flow, then there's a possibility for it to be unstable. Okay. And so what's an inflection point? So an inflection point is any location in the velocity field where the second derivative of the velocity is 0. And so the question that you want to ask for Rayleigh's criterion is that, is there any location where the velocity profile, or I should say the second derivative of velocity, and so if you're going to determine stability using Rayleigh's criterion, all you have to look for are just the inflection points. Okay, any questions on this before I turn the page? Okay. So I've kind of talked about inflection points quite a bit, but I don't think I've actually ever drawn one. So let me kind of draw that for you guys. Okay. So an inflection point is somewhere where the second derivative is equal to 0. Okay. So the one, excuse me. So the kind of the big question. So the d squared u dy squared equals 0 is an inflection point. So the inflection point actually specifies a physical location. So it's not that d squared u dy squared is equal to 0. It's the location where d squared u dy squared equals 0. That's the inflection. Right. So kind of the most common locations, or the most common places where you can have this is if you have any kind of backflow in your system. Okay? So let's say that we have a velocity distribution that looks like this. Actually, let me draw this a little bit better. Okay. So say we have a velocity distribution that looks like this. So on the bottom half of the domain, the velocity is going from right to left, and then from the top half of the domain, the velocity is going from left to right. Okay? So on the middle here, you kind of have this change of directions. So if you actually compute the second derivative here, what you'll find out is that because you have this kind of change of direction here, you should see it's equal to 0. And so conceptually, the way that you can think of that is that another way to express the second derivative is like this. Okay. So it's the rate of change at which the rate of change of velocity is changing. Okay. So du dy, we know that's the rate of change of velocity as you move in the y direction. Okay. So once the rate of change of that is equal to 0, then that's an inflection point. And so kind of with that in mind, what I asked you to do for the homework is kind of a very unique case. While it's true that you can make the second derivative equal to 0 in the homework, okay? And the way that we did that was basically adjusting the slope of the ramp until it was 0. What was unique about that flow, and which is actually not indicative of a lot of flows, is that once we set the ramp at that height, the second derivative of velocity is going to be 0 everywhere. Okay. Or in other words, there wasn't any location in problem 2 where we found where we had a second derivative of velocity not equal to 0, and that's kind of a direct result of the physics in that problem. So it's kind of unique. So in a lot of practical cases, you're not going to have the entire second derivative equal to 0 for the entire way. Okay? So let me kind of just do a very quick example on the next page to kind of show that. But before I do that, are there any questions on this? All right. So the question is, which method is normally more reliable, Rayleigh's or Fjortoft? So yeah, it's okay. It's a hard name. So Fjortoft is generally more reliable. So you can even determine that just from the verbiage of how they describe those theorems. So if you kind of look at the description of Rayleigh's theorem or criterion, what you see is that if you have an inflection point in the flow, then it's possible that there's an instability. But if you look at Fjortoft's theorem and said if that is satisfied, then there is an instability, or it's more likely that there's an instability. So if you can compute Fjortoft's, then that's usually more reliable. But the reason why we don't just use Fjortoft's is that there's usually more involved. It's usually more involved to compute Fjortoft's criterion, because straight from your velocity distribution, it's pretty easy to determine if you have inflection points or not. So that's why Rayleigh's is still kind of used, because it's because even if it can't be used to determine if you have an instability, you can use it to rule out the possibility of an instability, right? So if you have a flow that doesn't have any inflection points at all, then by Rayleigh's criterion you can say that this flow is going to be definitely stable. Yeah. Okay. So let's do just at least a partial example to kind of show you, okay? Because actually under a lot of the normal circumstances that we solve our problems, we solve basically just Poiseuille type problems and Couette type problems. It's actually impossible to get an instability. And if you kind of read kind of the end of the lecture notes at that section, you'll kind of see that too, where if you have kind of Poiseuille flow or Couette flow, under Fjortoft's theorem, it's impossible to actually get an instability. So the cases where you can get an instability are cases where if you have like a boundary layer with an adverse pressure gradient. Okay. And so let's say that we have a situation where we have flow into a model or into a surface, and let's say that we know what the pressure gradient looks like. Okay. And so let's say that we have some kind of really weird pressure gradient. And let's say that we know that it's equal to, I don't know, let's say sine of 2 pi t over L, something like that. Okay. And so what we can do is we can take this pressure gradient and plug this into Navier-Stokes. Okay. And so let's assume for a second that we have a steady flow, and that we have a fully developed flow. Okay. Sorry, this is not T right here. This should be Y. And so if we assume a steady and fully developed flow, and let's say that we'll ignore gravity too. And so if you kind of run through all the typical cancellations that we do in Navier-Stokes, what you'll see is that we only have two terms that survive. So we have basically 0 on the left-hand side. That's where our unsteady term and our convective terms are. And on the right-hand side, we have -1 over rho dp dx, okay, plus nu, okay, d squared u dy squared. All right. Well, in this case, we know what the pressure gradient is, so let's go ahead and plug that in there. Okay. So, and then let's move that to the other side of the equation. So we have 1 over rho times sine of 2 pi y all over L is equal to nu d squared u dy squared. And so you can see for this case, you know, we have a situation where, you know, our second derivative of velocity is not going to be just either 0 or not. So it's going to be a function. Okay? So if we kind of move the viscosity over to the other side, we can actually plot that d squared u dy squared, and we can see that we have, you know, explicit locations where an inflection point will occur. Okay, are there any questions on this before I show that? Okay. And so if we move the viscosity over to this side, what we get is d squared u dy squared is equal to 1 over nu sine of 2 pi y over L. Okay. And let's plot this as a function of y. Okay. So I'm going to do something weird. So I'm going to put the y-axis on the x-axis just because I can draw sine waves this way, but it's hard for me to draw sine waves that way. And so if we actually draw this out, it looks like this, okay? Where this is L right here, okay? And on the y-axis here, we have d squared u dy squared. And so you can see in this case, we have cases where our d squared u dy squared is positive, okay? And we have places where it's negative. And then we also have locations where d squared u dy squared is equal to 0, okay? And so because we have locations where d squared u dy squared is equal to 0, these are going to be our inflection points. And so notice how this is different from the homework problems, because in the homework problem, what I asked you guys to find, or basically under the conditions of the homework problem, basically what we have is d squared u dy squared is 0 everywhere. So you don't really have an inflection point, you can have an inflection region. So that's kind of not exactly the same thing. So in order to have an inflection point, you kind of have to have places where the second derivative of velocity is not going to be equal to 0. And so that's kind of exactly what we have here. Oops. And so actually the ones that probably are going to be most interesting are going to be, actually all of them are going to be interesting. All these inflection points are going to be interesting. So because of Reynolds criterion and because we have inflection points here, we can say that there's a possibility for this flow to be unstable. Okay. All right. Any questions on Reynolds criterion? Okay, so let's talk about Fjortoft's theorem. Okay. So Fjortoft's, you can kind of think of it as kind of an extension of Rayleigh's. So Fjortoft's is usually a more reliable way to determine if there's an instability or not. Okay? And there's basically just one formula that you need to know for this. Okay? So it's basically U minus UI times d squared U dy squared. And this has to be less than 0 in order for you to have an instability. So if satisfied, then we have an instability. And so let's label each of the different parts of this formula here. So first we have U. Excuse me. So this U right here is going to be this is just our general velocity distribution. Okay. So let's say that we took the previous equation here, and we integrated it twice, and we solved for the velocity. And then if we did that, then we get U of y. Okay. So kind of just the normal process of solving these kind of steady laminar problems by integrating the Navier-Stokes, that's what you would plug in for this U. So I know it looks like kind of a U that's a constant here, but it's you're going to plug in your full velocity distribution. Okay. Okay. And so the next thing that you're going to plug in is going to be UI. So the reason it has kind of a subscript I is basically we're saying that this is a velocity at a specific location. Okay? And that specific location or locations is going to be at the inflection points. Okay. And so, you know, if you look at the previous problem or the previous kind of example here we have kind of 3 inflection points. So we have one at the wall, we have one in the middle, and then we have one kind of at the far side. Okay. And so at these 3 locations, we can evaluate the value of the velocity itself. Okay. And so when you plug into Fjortoft's theorem, you're going to plug in the value of the velocity at those 3 locations in for UI. Okay. So you're basically going to get 3 different relationships or 3 different evaluations of Fjortoft's where you're going to evaluate this at every inflection point. Okay. Right. And then the last kind of aspect of Fjortoft's theorem that you need to include is this d squared u dy squared. Okay. And so what you're going to plug in for that is going to be your general second derivative. Okay. So if we go back a second to the previous problem, okay, we can see here that we have d squared u dy squared is equal to 1 over mu sine of 2 pi y divided by L. Okay. And so to apply this to Fjortoft's theorem, you're going to take this entire expression here and plug it into here. Okay. So there's 3 terms that you need to do here. So there's u. So u is going to be our general velocity distribution. D squared u dy squared. So that's going to be our general second derivative. So usually those are going to continue to be functions of y. And then you're going to subtract u at I. So ui, remember that's going to be the value That's a single value of velocity at the inflection point. Okay? And so after you plug all those in, and then you can basically determine to see if that function is going to be less than 0, or if there's going to be any location where it's less than 0. If that's true, then if Fjortoft's theorem is satisfied, then you have an instability. Right. So any questions on this? So after this, I'll kind of show you how that applies to the to problem 2 on the homework. Right. So that's a great question. So the question is, what if Fjortoft's theorem is not satisfied, but Rayleigh's is? So that's actually the exact situation in the homework. So in the homework, basically, you have Rayleigh's criterion, which says that there's an inflection point in the flow, but then when you actually plug into Fjortoft's, it's not satisfied. Okay? And so in that case, when there's a disagreement between the two, you tend to agree more with Fjortoft's theorem. So if Fjortoft's theorem is not satisfied, then you say that the flow is not going to be unstable. So Rayleigh's criterion is kind of like a weak check to see if it's going to be unstable, and then if that's satisfied, then kind of the next check that you do is Fjortoft. And so if Fjortoft is not satisfied, then you know that it's not going to be unstable. It's going to be stable. Yeah. There's kind of a lot of double speak and a lot of double negatives that happen. So if there's a disagreement, then kind of listen to Fjortoft's, because his is a bit more reliable than Rayleigh's. Any more questions on this? Okay. Okay, so then how does this apply for the homework? Okay. And so for problem 2 in the homework, basically what you found What you should have found from the homework, from the earlier parts, was that u of y is equal to 0 everywhere. And also that d squared u dy squared is equal to 0 everywhere. Okay? And so when you plug these guys in to Fjortoft's theorem, what you get is u of y minus ui times d squared u dy squared. Okay? And that should be less than 0. So let's plug in 0 for these guys. Okay, so you have 0 minus ui times 0 is less than 0. Okay. Since we don't have an explicit inflection point, basically we have that the second derivative is equal to 0 everywhere. Basically, this ui is going to be 0 as well. Okay. And so when you work out the math, what you get is 0 complete on the left-hand side, and you have 0 that's still on the right-hand side. So you basically have 0 is less than 0, which is not possible, unless you're kind of a really weird theoretical math person and you can prove that. I am not. So when I say 0, when I see 0 is less than 0, then I know that that is a lot of bullcrap. So that's not true. So Rayleigh's theorem or Fjortoft's theorem is not satisfied. So this tells us that our flow is stable. And so this is a case where you do have that disagreement. So you have Fjortoft's theorem saying it's stable, whereas Rayleigh's criterion is saying it's unstable. So in this case, the flow is going to be stable. And so in part F, or I think it was part F, or the very last part of that problem, I wanted you to basically, interpret these results. And so you have a disagreement here. So, which one is more reliable, right? And so to kind of help you out with the reasoning, I kind of want to box this one right here. And so if you have a velocity field where it's equal to 0 everywhere, basically what that tells you is that the fluid is just totally at rest. Okay. So basically it's the same as if you had a glass of water on your table, right? So if a fluid that's at rest, there's basically no way for it to become unstable, right? Because instability happens due to flow, right? And even if you have like a glass of water on your desk, you can even look at it, right? There's at no point, unless you shake the table, does that glass of water going to become unstable and just suddenly splash you in the face. At least not in the world that I live in. you know, it makes sense that if you have a fluid that's completely at rest, then you don't have any, then it's not unstable because there's no way for any turbulence to occur. Okay? And so that kind of, you know, paradox that you can kind of say it, it's not picked up by Reynolds. Because Reynolds basically saying is that if you have u of 0 is equal to, u of y is equal to 0 everywhere, then you have an inflection point. So you should have an instability. But when you plug it into Furtov's theorem, Furtov's basically say like, no, that's, you know, that's a load of BS. You know, if you have flow that's at rest, then flow that's at rest is stable, and that's kind of what's that's what is confirmed there. So it's kind of like a, you know, the kind of the purpose of that problem is to kind of get you to kind of plug in with, or to play with Reynolds and Furtov's, and to kind of take a step back and kind of think about, you know, what it actually means for flow to be unstable, especially when you have flow that's at rest like that. Okay. All right. Are there any questions on that? Right. So so the question is, in the previous example, how do we get ui by plugging the values of where the sine term was equal to 0? Right. So that's a good question. So to get ui, we basically know that the second derivative is going to be equal to 0 at 3 locations. Okay. So the 3 locations are going to be y is equal to 0, y is equal to L over 2, and y is equal to L. Okay. So these are the locations of inflection point. And so once you've determined the locations of the inflection points, what you're going to need to do is you're going to need to plug that into u of y, right? And so after you basically integrated this d squared u dy squared, you're going to get a function u of y. And so in order to get ui, what you need to do is you need to evaluate. There's no space anywhere. I'll do it on the next page. So in order to get u of I, you're going to evaluate the velocity at 3 locations. Okay. And so ui is basically going to be the value of the velocity at y is equal to 0, at y is equal to L over 2, and y is equal to L, because those were the locations of our inflection points. Yeah. So you're going to evaluate basically Furtov's 3 different times, one for each of these locations. All right. Any final questions on this? Okay. A slight typo. Oh, in the problem. Maybe. I'll double check that, and I'll get back to you on that. I think Naveed found he found kind of a sign difference in that, but I'll double check the symbols to make sure that they all match up. Okay, so we're basically out of time. So I just want to take just since this is kind of our last time all together like this, I just want to take this moment to kind of thank you guys for a great semester. So I know it was in a semester that was far from ideal. You know, we spent basically the second half of the semester teaching virtually, and I know that this kind of form of teaching is, you know, very far from perfect. You know, you ask any teacher, and, you know, we all prefer to kind of have things in person because it's you know, things are a lot easier that way. So you know, and I think from your guys' perspective, I know that, you know, everyone here has been working extremely hard just to kind of make the best of the situation. And, you know, make no mistake that it was it was you know, this is kind of a crappy situation that we're all in. But, you know, I really want to thank you guys, because, you know, just through all your guys' hard work and through all your guys' kind of perseverance, you kind of made this class kind of as best as it could for me as well. So, you know, I think there's kind of a, you know, I always tell my students that there's no class without students, and I think that's kind of especially clear right now. So, you know, I could have very easily just kind of sat in front of my laptop and just kind of talked to my laptop screen, and, you know, but that wouldn't be teaching, because there wouldn't be students there. So the fact that at least you guys are at least here virtually and, you know, asking questions and participating, that's really made this kind of as good of an experience for me as well. So, you know, I really want to thank you guys for, you know, all the work that you've done, and, you know, you know, what I hope is that, you know, hopefully this class, you know, you take something good away from it, and you learn, you're at least a lot more excited about fluid mechanics than you were beforehand. So, so thank you again, everyone. You know, we still have our final exam, so that's going to be next Wednesday. But, you know, I just want to thank everyone again. So please have a good evening. You know, please stay safe this summer. And, you know, if there's anything that, you know, I can help you with, you know, whether related to fluid mechanics or, you know, anything with the university or anything else, then, you know, definitely shoot me an email. My email is always going to be open, and, you know, I'm always, you know, happy to have a Zoom call for anything. So, you know, I wish you guys all the best, and, you know, please stay safe and please stay healthy out there. Yeah, thank you guys too. Yes, yeah, so the final is going to be on Wednesday. So I think that's Wednesday, May 13th. So it's going to be a 24-hour midterm. Yeah. So I'm not going to curve the class in the traditional sense. So what I'm going to do at the end is I'm going to take a look at the class average, and if the average is kind of lower than a B, what I'm going to do is going to add points to everyone's grade until the class average is at that B. So, you know, for individual cases, I think probably I'll discuss on an individual basis, but at least, you know, at least kind of as overall as a class, that's kind of what I'm looking to do. But I know that there's definitely some individual cases out there. So if you want to talk to me about your grade, kind of more in private, I'm definitely open to that. So the question is, am I still going to have office hours? Yes. Yeah, so next week, I'm still going to have my regular office hours. So I'm going to have Monday, Tuesday, Wednesday office hours. So none of that's going to change, especially because our final is going to be on Wednesday. And so, but if you want to talk, you know, outside of office hours, you know, just shoot me an email. I can literally sit in this chair for like 15 hours a day. So, you know, if you can keep me company for, you know, 20, 30 minutes of that, that's actually, you know, a good thing. We can talk about fluid mechanics or anything else. So I'm always happy to set up a Zoom call at any time. So the question is, this review session to be uploaded as well as the 5:30 session? Yes. Yeah, both of those are going to be uploaded. So I personally have the video file for this review session, so I'm going to upload that myself. But Dr. Sanders has the video for the 5:30 session. So that was the research seminar. So I've already asked him for the video. I think he's going to download it from Zoom and then send it to me. And basically, once I get it, I'm going to upload it to my YouTube channel. So you'll have that available for you as well. All right. Oh yeah, so that's a good question, Ron. So yeah, there'll be 6 short answer problems, and then for the problem solving questions, there'll be 4 of them. So basically, compared to the midterm, there's 2 extra short answer and then 1 extra problem solving. Yeah. So in total, it's like roughly 50% longer than a midterm. Yeah. And that's kind of a reflection of how much time that we usually have for the final.